So the presentation agenda is that I first tell a little bit about the standard physics model of the scalar field. What is it officially, and how it has to comply with very strict standard physics rules, and that you can deviate from those rules. Then I will talk a little bit about flaws in classical electrodynamics theory and how to fix those flaws. And then you get a theory that's less strict than the standard model. And I will present a generalized electrodynamics theory that also includes scalar fields, because that's the topic of the conference, and that it also fixes a couple of flaws. And then I would like to present some experimental evidence for that, but on a qualitative way, still not quantitative, that you do exact measurements. And then some conclusions. So that's the agenda. And next slide. Okay, we have a very official scalar field according to CERN and the physics community, and that's the Higgs field, the well-known Higgs field with the Higgs boson. The Higgs boson has a spin 0, and that's why it is a scalar boson, while all the other bosons and fermions have spin 1/2 or spin 1. So that's a clear difference from the other particles. And the Higgs field is a scalar field, and it has an imaginary mass, and I don't know what that is, but it appears to have imaginary mass, and it's not electrodynamic in nature. So, but the Higgs theory and mechanism, it satisfies the following theoretical principles. It has to be renormalizable, that's a bit of a difficult word, renormalization, that's a particular physics principle. And it is also a gauge symmetry breaking of the U2 gauge group, also difficult to understand. But if you would have a U1 symmetry breaking of the U1 gauge group, then you would have an electrodynamic scalar field and scalar waves. But that's not the case with the Higgs field. It does not violate Einstein's causality principle, so no superluminal signals that are carried by the Higgs field. What is renormalization? It is a mathematical technique for removing infinities from calculations of physically measurable values. So that's something that is finite if it's measurable. And also in the relativistic field theory. And superluminal means faster than the speed of light in vacuum. So that's the other term that I should explain a little bit. So the question is, are these principles correct actually in practice? Is this really physics? So anyway, these principles rule out the development of an electrodynamic scalar field as a symmetry breaking of U1, and then you get electrodynamic scalar fields. And they say, the physicists, this is not observed, and also the photon would acquire a mass, you know, and that's also not observed. But this is all according to these very strict principles. So however, are these two principles even valid? So next slide, please. And the renormalization principle was first applied in QED and QFT theory. But if you have a closer look to this technique, then it starts to be a bit uncertain. So one of the principal authors of QED theory was Freeman Dyson, and he published a paper after the whole QED theory was published, an after paper, how that the whole principle is actually meaningless. So he proved that mathematically. A quote from his paper: all the power series expansions currently in use in quantum electrodynamics are divergent after renormalization of mass and charge. That means that this QED theory and normalization only predicts infinite values and not finite values that you can measure. But that is actually what this says. So it is a meaningless theory, actually. And there is another author on QED who investigated the history of very high precision experiments that confirm the QED theory. That's the G factor of the electron. Mm-hmm. And this is also a very strange history. And Oliver Conza, he concludes, it was evident that the QED calculations had matched the experimental data because they were manipulated. And that you can clearly see in the history of these values. The high precision predictions by QED theory of experimental data are based on fraud, actually. So this was Oliver Conza's conclusion. So that's not very good, actually. So now you have two reasons to really doubt this whole normalization technique. So then we can actually drop that principle. And so it's actually a meaningless procedure. Okay, next slide, please. And then we have that other principle that we have to doubt, the Einstein causality. And that was derived from special relativity theory. And signals cannot have a velocity at particles that faster than the speed of light. But anyway, more modern experiments show that this principle can be violated. And very interesting new experiments are the Coulomb force propagation measurements. And these measurements show that the Coulomb force, which is also in Weber's law, by the way, is very much faster than the speed of light, is instantaneous. And about 10 different types of experiments showed that this is the case. So this is clearly in violation of Einstein causality. That does not mean that causality itself is violated, but anyway, Einstein's idea about causality. And another type of experiment that shows superluminal velocities is photon tunneling is the tunneling of photons. And these are experiments by Gunther Niemtz. And this also shows that there are signals that are faster than the speed of light. And the third type of experiments that are in disagreement with Einstein causality is electron tunneling measurements. And this also shows that electrons that are going through a tunnel, are tunneling through a barrier, I should say, have a velocity that is faster than the speed of light. There are a couple of experiments that show that. So, in particular, the superluminal speed of the Coulomb force is manifest on the microscopic scale, but actually it's in agreement with QED, if it still can talk about QED. But it's also manifest on the macroscopic scale. And for that reason, we have to look again in Maxwell's classical electrodynamics theory, because here we have a flaw of Maxwell's theory, because this is in disagreement with the Maxwell theory as well. Okay, and we're going to the next slide. And so we have to review Maxwell-Lorentz theory to see if there are flaws in it. So one of the flaws that you can see that top down is the Coulomb force propagation is much faster than the speed of light. But if we look at the Yefymenko field expression, which is to your right, the expression of E, and then a lot of terms behind it, then the first term in the integral says it has Tc. And that means that the Coulomb field has the velocity of c of light, and which is in clear disagreement with experiments. So that's a flaw. And another flaw is unexplained longitudinal electric far fields, which are the red terms at your right, at the Jeffimenko field solutions. These are unexplained actually by experiments outside the, let's say, what is known about the transverse waves. And a third law is the Lorentz force law, and also the Grassmann force law, is in disagreement with Newton's third law of motion, and that's violated by the Lorentz force law, also indicated by Dr. Assis. And so we have a couple of flaws. So we have to fix that, actually. So in the next slide, please. So a very simple fix of this theory is to introduce a little condition which has an impact on the whole theory. And that's the condition in blue. And what does that tell? What does that condition means? Actually, that divergent currents that are also dynamical cannot be a source of divergent electric fields, because this time differential of the A potential, the vector potential, that is actually included by Maxwell, because this was generated by dynamic currents that are rotational and also varying in time. That's actually the Faraday law, which is responsible for this term in the electric field. But is this term, if this cannot be divergent, because if we have no experimental evidence for that, then we can exclude it from the theory, actually. So then we have an extra condition. Then all the field equations change a little bit with this extra condition. For instance, the Gauss law becomes a Poisson equation for the electric potential. And that means that the Coulomb field becomes instantaneous. It's no longer a wave function that propagates with the velocity c. It now becomes instantaneous. And that we can see in the Jeffimenko general field solutions. We now have a Coulomb field term that is instantaneous. That's no longer delayed in time. There's no time delay to it. And also these red terms that I mentioned before are also disappearing from the equations. So now it's much more balanced, much better theory, except of course for Newton's third law. And that's still violated also by this theory, so it's still not perfect. Okay, now we go to the next slide. So this was a simple fix. Now I would like a much better fix for these problems. And therefore we have to introduce scalar fields, which is after all the topic of this whole presentation. And I have defined two types of scalar fields that we have to introduce. These are here. And these are the normal electric and magnetic field. But then we have two types of scalar fields. And I have to introduce now another type of velocity, which is represented by the letter A. And A is much faster than C. And so I have two types of scalar fields here. And in your presentation, it was had the letter S, you know, of scalar field. But you only had one type of that expression. And I have included a different expression with the velocity A in it. So you can indeed, in a similar way that you showed, add the scalar field derivations to the field equations that you can see here, BE and BC. But now I have two types of it. And this is motivated by these modern experiments that show the Coulomb field is superluminal. It's much faster than the speed of light. So we have now two potential equations. One is traveling with the c velocity, and the other one is traveling with the a velocity. And then you get a much richer electrodynamics, which you see at your right-hand side, generalized field solutions, and especially the green and the blue terms are now scalar electrodynamic waves where the electric field component is longitudinal. So this goes together, that you have a scalar field and a longitudinal electric field together that form a wave, actually. And, okay, what can I say about that? There are two types. The green one is a superluminal type of longitudinal electroscalar wave. And, oh no, sorry, that's the luminal type. It's the other way around. And the blue fields here are superluminal. So we have two types of waves. And for that reason, they cannot cancel each other out. Because if you would make A equal to C, then you have also two types of waves that have the same velocity. And now A becomes C. And then these waves cancel each other out and they disappear from the theory as well. Mm-hmm. And this was explained to me by a colleague of Harold Puthoff. He is also a well-known electrical engineer. That this is the case, that these waves could cancel each other out. So, but now with these modern experiments of the superluminal Coulomb field, that cannot be the case anymore. So, this also leads to the Whittaker force density law, which is shown top right, Whittaker force density, where we have an extra term in the force, which is a scalar field force, but also a longitudinal ampere force. And this restores some of Newton's third law, but only the linear momentum and not the angular momentum. So it's still not perfect, and still we have to reconsider Ampere's law, but it's a step in the right direction, I would say, because it restores linear momentum, but it's still not perfect. So we have a couple of fixes, and also the 4/3 problem, which is also a famous problem in electrodynamics, is also fixed by this theory, but that's too lengthy to show here. But I've made some calculations according to an American physicist with the name of, what was his name? I forgot. But I repeated his calculations, and that really shows the 4/3 problem is fixed as well. Mm-hmm. And so that's not bad for a revised theory that includes scalar fields. So that's an indication that we are on the right track here. Okay, please, next slide. Here we have a continuation of this theory, and I have a power and a force theorem that shows that the scalar fields are actually physical. You know, that we have an extra term in the power theorem, that's the top equation here, that we have extra scalar field components that represents power, which is something that is physical, and that represents forces, which you can also measure. So we have now a much more physical theory that includes scalar field effects that you can measure, actually. And so this is based on three types of electrodynamic waves. Now, first, with the Maxwell theory, we only had one type of electrodynamic waves in vacuum or in guided by a media or so. Can also be a material medium. And that's the transverse electromagnetic wave, which I've shown a picture at your right. But now we have two extra longitudinal waves. One is luminal and the other is superluminal. And because the scalar field in the superluminal wave is dominant, because there's also an electrical component in that wave, but the scalar field is more dominant, more stronger. I call it a scalar field wave. And it's necessary to do experiments that also proves the existence of these superluminal scalar field wave. Therefore, we have to think of experimental data and that we have falsification or verification of this idea. Okay, next slide, please. Next slide. Is it not going? Yeah, okay. So first I would like to point out an experiment that has been done by Tesla and also by a Russian team, which is about energy transport over a single wire. And the results of these experiments is that you can transport a lot of energy in the kilowatts over a single wire, which can be very thin, and over longer distances, and the wire material does not seem to matter that much. It can be copper, aluminum, steel. So there's something going on with this system. And there is no earth return. That means it's just a single wire without a return wire, which is more the traditional way of energy transport. So at your right-hand side, there is a more traditional situation of power flow over a copper wire. And that power flow is based on the Poynting vector. And that's the cross product of E and B. And for this we have to have surface charges and drift current that source electromagnetic fields, but in a traditional way. So this is only for a 50 or 60 hertz system, and for DC systems. Then we have that situation at your top right. And for this we have to have drift current in the copper wires. And that also means we have losses. Because if we have drift current, we have Ohm's law, and we have a waste of energy, actually. And so that's not ideal, but still very good. About 10 or 20% losses in the electricity system. But now we go to the physical situation for the single wire transport. And because the frequencies are much higher in this system, we have almost no drift current. That's also called the skin effect, that we have no drift current left in the copper wire. But we have much more dynamical surface charges in this system. And we clearly have also divergence and convergence of those surface charges because they are so dynamical. And that might create a scalar field, actually, and also a longitudinal electric field which is derived from the scalar field, which is actually the time derivative of that scalar field. So we have now a totally different type of power flow, which is represented by the green arrows. And we see the electric field, it changes orientation all the time. And that's the blue arrows. They go from to the right and then to the left. But if you multiply this with B, which is a scalar factor, then you end up with a unidirectional flow of power, actually. So that's a way to explain the power flow over one wire. And then you have also an explanation why it's lossless. There's no losses, no lost energy, because there is no drift current, so there is no generation of heat, and it's only based on surface charges. So that is some experimental evidence for this type of wave, actually. And here we talk about the luminal wave. Now, so I would like to point out some evidence for the superluminal wave in the next slide. In the next slide, please. So we have also energy transfer by means of superluminal electrodynamic scalar waves. That's a whole mouthful. But the difference here is that the wave is much faster than the speed of light. So we get a different type of wave that has no momentum in it. So the photon has still momentum and energy, but this type of wave only carries energy, but very little momentum. And because the ratio of that must be equal to A, to the superluminous velocity itself. And if this A is much bigger than C, then we also have very little momentum. So for that reason, the superluminal scalar wave will change only the potential energy of particles. If particles receive or send those waves, then only the potential energy is changed because there is no momentum involved in this kind of interaction. So that's a clear difference with a photonic interaction. But since the rest energy of a particle is also a form of electric potential energy, and okay, maybe within the Weber theory it's a bit different, that we also have an effective mass and so, but according to the standard electrodynamic mass theory, then mass is also a form of potential energy, of electric energy. So that could also change by receiving this type of scalar field waves or sending them out. So in order to receive or send this type of wave energy, the particle must be in superluminal motion. So this is just a suggestion that only superluminal matter can receive superluminal wave energy. So there must be, you can also call it impedance matching, something like that. So I've depicted that at the right-hand side, that you have a form of, that you have quantum tunneling involved, because that's the superluminal motion of the particle when it's going through a tunneling barrier. So therefore we need a tunneling barrier to receive or send those waves. So this is an important clue to work with this kind of energy. So we need quantum tunneling in this process. So, but the difference with the more classical picture of quantum tunneling is that the potential energy is asymmetrical. So before the tunneling it can be lower, and after the tunneling it can be higher, or vice versa. You see these different in levels. So that means that the electron or the particle will have a changed potential energy after the tunneling effect. So that is a way to work with this type of electroscalar waves. And so this is something to keep in mind. And there is also a connection with zero-point energy. What is zero-point energy? That might be a background radiation that consists only of those superluminal scalar waves, instead of, for instance, luminal TEM waves, of transverse electromagnetic waves. So that's my opinion, what the zero-point energy actually is. And it is also a connection with pilot wave theory, because Louis de Broglie, he described this pilot wave also as a superluminal wave, and which has an interaction with the matter wave. So this is it's also called the dual wave solution, that we have a superluminal wave which is interacting with a particle wave which is subluminal in velocity. Then we have papers by Anthony Valentini, and he describes that in this interaction of particles and superluminal waves, we can have a non-equilibrium or we can have equilibrium. And if there is equilibrium, then Born's rule applies, but in situations where there is no equilibrium, then Born's rule cannot be applied. So then we have a generalization of quantum mechanics, actually, where Born's rule does not apply anymore. So that I think that also applies to the situation at your right hand here, where the potential energy of tunneling particles will change. So that is clearly an indication of non-equilibrium, where the particle can pick up energy from the 0-point energy background. So that's, I think, an interesting hypothesis how we can extract 0-point energy from the vacuum. Okay, please, next slide. So here I have a couple of two examples how what I told before applies to a device. That we have some type of quantum tunneling, and all of a sudden we have more energy. So the first device that I would like to discuss is Dr. Garrett Model's micro device. And it clearly has a tunneling barrier, which is here, this small layer here, the insulator model. Electrons tunnel through this insulator model from the upper electrode to the base electrode, and then the electrons can flow back through the measurement circuit to the beginning. So Dr. Model concluded that this is a 0-point energy extracting device or harvesting device, but the total amount of power is only microwatts, so very little power. But anyway, it keeps on going indefinitely. So there is no external battery involved or external power supply. It's just a device which will go on forever and all by itself. So the 0-point energy is driving this device. He claims also that this optical cavity is important to have the Casimir effect involved. But I am a bit doubtful about that, actually, because I don't see why it should have a big effect on the electrons here. It can have an effect, but I have my doubts if this really is the Casimir force effect. But anyway, it works. It's a system that's also based in quantum tunneling. That's very important to remember. So a much more practical device would be Henry Moray's 0-point energy harvesting device based on vacuum tubes, which was already displayed in 1926. That's almost a century ago. And this device had a very good review of physicists and patent office clerks and so on. They inspected this device and they could not find any fraud or foul play. But anyway, this device was about kilowatts. So that's a whole different ballgame then. It's about 1 million times more energy output than Garrett Model's small device. So this is really interesting. If it could work, then that could be a real difference for us all. But I've analyzed the physics of this device, which is very interesting. And in these vacuum tubes that were applied by Moray, they were applied in an unusual way. So usually vacuum tubes work because we heat up the cathode, and then we get thermionic emissions of electrons from the cathode into the tube itself, into the vacuum. But Moray, he applied high fields. Dus he didn't heat up the cathode, but he just used much higher voltages, a high field emission, that's called. It's high field emission. And if you look into the theory of high field emissions of electrons, then it's very clear that it must be based on quantum tunneling again. And this is, the technical term is Fowler-Nordheim tunneling. And this happens always when you have electrons emitted by a cathode by means of strong fields. And you automatically have quantum tunneling as well. And that might, that corresponds with my principle that you can pick up zero-point energy by means of a superluminal motion in quantum tunneling barriers. So that applies also for this device. So now we have a little bit of a physical explanation why Moret's device worked actually. And down in the pictures below, you see that Moret applied a transformer, a high-frequency transformer, the SM220, and that's also in the diagram there. So in the diagram we have the round things are the vacuum tubes, and the transformer symbols, that's the thing over there. And then there was also a couple of tunable condensers, or capacitors I should say, and a device which Moret made himself, the Moret valve, but that's not really essential, I think, in this picture. The essence of this free energy device, let's call it a free energy device, is that the electrons are emitted from the cathode by means of high fields, and not by heating the cathode. That's the essential difference. So this is very interesting and something we could replicate, and we could do some more experimental work to replicate this device. Okay, so that's another example of harvesting scalar wave energy, actually. Next slide, please. And then we have a different topic about, I told a little bit about the mass of a particle that might also change. And of course, if we have to increase the mass of an electron, then you have to add energy to it. So if that energy is scalar wave energy, then you do not add momentum to the particle. So that is an important mechanism that might explain low energy nuclear reactions, actually. Because we have to fuse an electron with a proton in this process, and the electron must not get a relativistic velocity in the process. Otherwise it cannot fuse with a proton. So we have to have an electron that picks up scalar wave energy, then it stays very slow. And then for that reason it can fuse with a proton. And also the resulting neutron also has a very low velocity. And that is something that could be combined with a theory by Witham and Larson. It's a theory about how LENR works. But the missing ingredient, in my opinion, is scalar field waves. And Moret actually showed that you can transmute elements by irradiating those elements with his vacuum tubes. So the radiation from his vacuum tubes, that was a kind of massless radiation that could penetrate through the glass. And then he had a couple of raw ores, or samples, raw ore, and he clearly could prove that the elements in those ores were transmuted to other elements. So this is a very essential, from a physical point of view, very essential type of experiment that really shows that there could be a massless form of radiation involved. And let's see, Kenneth Shoulders, that's another LENR researcher. He had electrons emitted from a sharp tip, But then you have to keep in mind that that process also generates quantum tunneling and might also be a source for scalar field waves. And Kenneth Shoulders also proved that you can transmute elements in this way by bombarding tin, for instance, a tin foil with his type of radiation, and he calls it. He thought it was an exotic object of a lot of electrons that were clustering, which actually is possible according to Weber's law. If those electrons come close together, very close together, then you can have an EV, exotic cluster of electrons, actually. But I'm not very sure if that was really the case, but I have a more alternative explanation for the transmutation effects. So, the last type of experiment that could involve scalar field waves are gravity impulse experiments that was shown by Podkletnov, and that also involves quantum tunneling. The sudden discharge from a superluminal disk that is also has the quantum tunneling effect in it, and according to my theory, this produces a very strong scalar field wave, which Podkletnov has measured the velocity of, and it's superluminal, about 64 times faster than the speed of light. But this experiment was never reproduced, so I have to make that comment. So this is not still very official science. But anyway, very spectacular. And he could show that it has a gravitational kind of effect on sample masses and so. So there is a link, maybe a link also with gravity. That gravity might be also a matter of superluminal scalar field waves. But a very, well, let's say, specific type of effect. And we still do not know very well what gravity is and how this can be linked with electrodynamics. But to do that, we have to involve a lot of other theories as well. And I like very much Eric Verlinde's theory on gravity, which is based on quantum information that's present everywhere in space, which can have a gradient, and not just a gradient. First, you have to calculate the entropy of quantum information, and that's like a kind of field in space. And from that, you can calculate the gradient, and then you have gravity. So that's a bit involved. But if you think of quantum information as superluminal scalar fields, then it becomes something that is engineerable. And for that we need this superluminal quantum tunneling motion, actually, which is actually displayed by the Podkletnov experiment. So that was maybe a bit of a stretch, but now we can have a little bit of an inclination towards engineerable gravity, which is also called, what was the name? I don't agree with that term.
Gravity shielding?
Yes, and reversed gravity or something like that.
Anti-gravity?
Anti-gravity, which is not such a good term, because we don't speak of electric fields or something like that, only because the direction is a bit strange.
Right.
So it's induced gravity, actually.
Podkletnov spoke about the shielding, right? Gravity shielding.
Yeah. So that is that can all be the consequence of this fix of electrodynamics. And of course there are also links to Weber's theory, I agree, because Weber's theory is a very essential theory from which you can derive also fields. There is a way to translate Weber's theory to a field theory, but that's a bit involved, that procedure. But Weber's theory could lead to more effects than predicted by Maxwell's theory. So it's a more general kind of theory, actually. Next slide, please. So I come to some conclusions that the experimental evidence confirms qualitatively the existence of electrodynamic scalar fields and of electrodynamic scalar waves and longitudinal electrodynamic waves, which is more or less the same. Huh? The longitudinal component is the electric field component. But the experiments are low in budget, so it's reproducible. It's not a CERN type of budget that we have to spend millions to detect a Higgs field. So this is reproducible, and it can have a practical value for new technology and for society. So I think it's desirable to return to fundamental research, the type of research that you are doing, which is not so expensive. So it can be reproduced by other teams as well. And that also can be meaningful and practical for society. And after all, the essence of the scientific method is that all experiments can be reproduced by others. And if that cannot be reproduced, can you still speak of science? Which is my criticism on CERN, actually. I don't want to be too harsh on CERN, but who can reproduce all these Higgs field experiments and so on? So we have to believe them that they are speaking the truth, actually. And, but, okay. And also we have to use Bacon's method of inductive reasoning, that's a bit of a philosophical angle here, in order to discover the essential laws of nature. This is also about discovering new essential laws. And inductive reasoning is a bit of the opposite of deductive reasoning, where you can deduce facts from fundamental facts. But now we have to look into new facts and try to figure out what the fundamental aspects are of physics, which is a little bit different from deductive reasoning. Mm-hmm. Okay, and thank you very much for your attention, all the listeners. And I hope it was interesting and that scalar fields can be very practical in the future.
Thank you, Koen.
Okay.
And thank you for watching. So, to my opinion, we will have now a little break, right?
Mm-hmm.
Very good. So we will continue with a QA session now. And so please ask your question using the chat on your website, scalar-field.com. Live. Thank you. So that was a very interesting talk. So I had a couple of actually questions, you know. So you were speaking about this about this surface charges, right? So in the slide where you were describing the this Russian team who were able to transport the energy over the thin wire, so you had some ideas. You showed the diagrams where you explained that it could be due to this different type of energy transfer than what we know from as Poynting vector, right?
Mm-hmm. Yeah.
Right. So this comes from your own kind of calculation, or you what was the motivation for the surface charge waves as you explained? That comes from your calculation.
Yeah. If you use very high frequency in such systems, then the usual drift current becomes practically zero, because we also have a skin effect. And the skin effect is actually that if you have very dynamic currents, then you have the lens effect in the wire, which cancels, that you create a secondary current in the wire, which cancels the primary current, actually. And this is called the skin effect. And you also only have very little drift current left, very close to the surface. But if you also apply very high voltages, so it's not just a couple of let's say 10 volts, but you are in the kilovolt range, then also your surface charges become very high. And if they are very dynamic, then only then can you use those surface charges for energy transport. So you both have to have a high voltage and a high frequency. But the Maxwell theory does not explain that very well, how the power flow can be unidirectional, so you have to have a scalar field type of magnetic field.
Right, but the skin effect is very well known, right? So this is a kind of the standard, I would say, phenomenon, right?
Yeah.
So I don't quite understand the reasoning that you would say if I just use a high frequency, then obviously the skin effect will be dominant, right? But that's not what these Russian people are claiming, right? You don't. It's not sufficient to have just high frequency, right?
No, you must also be high in the voltage, but if you have this skin effect, then you don't have a magnetic field around the wire, because there is no current flowing. The magnetic field is more or less cancelled, and for that reason you don't have any Poynting flow left. So that's why the standard electrical engineer in power engineering does not believe that a high frequency system can be used for energy transport, only for telecommunication. And for that you have two wires, and that you have an electric field that is pointing from wire to wire, a transverse electric field. But with a single wire you can also have these longitudinal fields, but that does not explain right away that there is a power flow over this wire. And for that you need this extra scalar type of magnetic field, which is overlooked by the standard engineer. So
yeah, I think that the single wire power transmission is so amazingly interesting. We have done also some experiments in our laboratory, and there is a lot of information of from AMI Innovation website, where Adrian Marsh has presented also a lot of very interesting experiments related to the Tesla transmitter with using a single wire method, and he also kind of clearly demonstrated that there are effects which he called, or it's known as a cold electricity, and this cold electricity, to my opinion, and what also Adrian Marsh, and we have also replicated some of these experiments in our laboratory, that it's somehow also related to gravity or whatever, because it seems to us that this cold electricity is capable also to generate extra force which acts on any kind of object, whether it's metallic or plastic or whatever. So it's very interesting, right?
Yeah, that's a bit new to me. So a new question? No, not a new question.
Right.
But also, if you have cold electricity, that simply means there is no dissipation of energy, and so there is no drift current in the wire. The surface charges are frictionless at the outside of the wire because they do not meet the atoms. And this was also confirmed by official scientists in the 60s or so, that the surface charges are frictionless. So if your whole energy transfer is based on surface charge only, then you have a lossless system, which can be very practical, of course, because we have now 10 or 20% losses in our electricity system, which is quite a lot, actually.
Yes, I think you are right. I must say that since then we are studying we are in this field, we are observing so many very strange phenomena that's right. Look, we have a question. Thank you for your presentation. What experiments are decisive for this scalar field theory, right? So,
well, I don't know what the most decisive experiment is, but for instance, if you talk about superluminal waves, then it would be nice if you could generate that wave and receive it somewhere else, and then you calculate the velocity. And that would show that you have a scalar field wave that is superluminal. That would be very essential or decisive. But also this single wire transport system, for which you can prove it cannot be based on Maxwell's theory, would also be decisive, in my opinion. So,
right. I don't want to stretch these questions too much, but I personally myself, I believe that since Nikola Tesla, so to speak, beginning of 20th century, 1905 or whatever, there are clear experiments can clearly demonstrate the presence of extra field, and I mentioned that during my talk that when Tesla was trying to replicate Heinrich Hertz experiment with radio frequency wave, electromagnetic waves, he was not able to replicate exactly what Hertz get because Tesla had he was much more ahead with the instrumentation. He has much better laboratory equipment, and he was not able to replicate Hertz experiment because I think he was observing already the the scalar component. He called it radiant energy or radiant field. Right? And so I believe that there are many experiments which can be used to prove that there is something beyond the standard model of classical electromagnetism. And
he was not right that transverse waves don't exist, because they exist both. So
you are right.
It's often the case when there is an opposition somewhere, then there can be both right, and then there is a more general theory.
That's you are right. That was the case. That essentially both Hertz and Tesla had a piece of the truth. Right?
Yes.
And so right.
But that doesn't mean that if we have this kind of scalar field, that the photon will acquire a mass. Because I want to repeat that again. That this is the official position of the physics community, that you cannot have these electrodynamic scalar fields because then the photon would acquire a mass. But that's according to very strict rules. And this is the explanation why the physics community does not believe in electrodynamic scalar fields. And so that's a bit of a mental obstacle only, because the official physics is also restricted by very strict rules that are not necessarily true. So,
thank you. There is also, to my opinion, very interesting question. Is there a problem with radiation to the environment with single wire power transfer? In other words, did it function as an antenna? Can it interfere with the communication? I have my own opinion on that, but maybe you go first if you want. You want to add something to it?
Yeah, I think if the single wire, if it has too much divergent electric fields, which are also, let's say, deflected or curved by, for instance, if the Earth is too close, then the electric fields can become curved towards another object or so. So you have to prevent that all these electric field lines stay straight. And then you do not have electromagnetic radiation that is transmitted by the whole wire. But you have to keep those electric field lines straight. And that's what you see in a normal antenna, for instance, a vertical antenna, that you have electric field lines from the top that are curved back to the Earth. And in this curvature, if you have a dynamic electric field, it will start to radiate electromagnetic waves. So Tesla also set up that you have, if you have a very high up terminal with a sphere very high up, then the electric field lines from that sphere must not be curved back to the Earth. And then you can have a system that will not produce electromagnetic waves. So that's my answer to it. It's both can happen. If you're not careful, you make a system that will radiate all the time.
Right. I just feel that that this question is because people might also be afraid of, nowadays there is this issue with G5 and also how dangerous the kind of the standard electromagnetic radiation, which is everywhere now in this technological society, what I would say. So if we are kind of now envision a new type of field, whether it will be kind of how this will interact with our existing environment, or it might be even danger and so on. My own experience is that there is so many very strange phenomena related to that, so it certainly deserves a lot of investigation and so on, but I know that there are people who are kind of exploring these high energy and high frequency phenomena for the kind of healing purposes. So it's that's another kind of interesting topic. But what we see in our laboratory also, that the electric, the lightning or kind of the electric discharge is changing its nature depending on obviously the voltage, but also the frequency. At some frequency, the discharge is very unpleasant, probably not very good for your health and so on. At the higher frequency, it changes completely the structure and it sounds now much more harmonic and so on. So I think we have no kind of definite answer to that question, but it's a subject of a lot of investigation.
Any type of technology can be used in a bad way and in a good way. And that's the same for this technology, if it really can be proven, of course. A lot of my talk is still hypothetical and needs more experimental proof. But it can, of course, be used applied in a bad way, that we become sick of it, or in a
maybe
good
this
way.
Interference with communication, right? So I just want to add that we are able now in our laboratory to switch off the electricity in the whole city, so that's kind of already, but that was not, related to communication problem, right?
No.
So, are we, right? Thank you for the very good presentation. What does a scalar field wave look like, or be schematically represented?
Yes, that's a very good one. If you Google scalar fields or scalar field waves, then you see the most beautiful pictures of people who say you can heal other people with it, but these are just pictures. So I have no idea how to make a good picture, how it looks like. Picture representation of a scalar field. That's more easy with a vector field.
Right.
But you can do that with colors and whatever.
To my opinion, if we are speaking strictly about the scalar field, it's something which resembles rather a sound, right? Because the sound we are hearing, is also propagating as a scalar wave, right? So it means the variation of the air density, let's say, right? So I know that some people are speaking about electric sound, right?
Yes.
Right. So
that would be a good alternative way to a scalar field or longitudinal electric wave.
Right.
That is some type of etheric sound.
Right.
And because the ether that was in the previous talk could still be some sort of a medium that's in empty space, so it's filled up with, let's say, etheric particles. Then the etheric particles can conduct transverse electromagnetic waves, but also longitudinal electromagnetic waves, like in any other material medium. Because a plasma can conduct both type of waves, and now I've seen on a long copper wire that we can also have both types of waves.
That's a good point, because I think for plasma physicists the longitudinal waves are very familiar with this concept. In plasma physics there is no problem, right, with the longitudinal scalar wave, so to speak. Right?
It's a kind of sound wave, but then in a plasma. But for the ether, it's only one type of wave, which is also a bit strange, and that's an exception actually. That the vacuum can only conduct the transverse wave, but I think that's wrong. But the vacuum, very often you see in a material medium that the longitudinal wave is much faster than the transverse wave. For instance, an earthquake wave.
Yes,
the longitudinal wave is faster than the transverse wave, and I think that's also the case in the plasma. So it's not a bad idea to assume that the scalar wave is much faster than the speed of light, because that's more according to what we observe already in material media.
Right. So, yes, I agree. So. What are the next steps in better relating Koen van Vlaanderen's general electrodynamics and Weber's law? Right, very good question. Where do the two theories meet, and what are the open questions? So I think it's a very good question, thank you.
Yeah, I have some ideas about this. I have looked into the method to translate Weber's laws into the Faraday law, that you can derive Faraday's law from Weber's law. Because Faraday's law is very much in a certain reference frame, and while Weber's law are not in a reference frame, because it's all relative vectors and so.
Right.
So you have to make a translation back to a system in a frame of reference, or reference. I never recall what's the right pronunciation, but you can do that also for the scalar waves and scalar fields, that you can derive them from Weber's laws, and I have some ideas about it as well. It's actually much according to the derivation of Faraday's law. That's more or less, but I think it can be done.
Right, and we were also discussing this magnetic field free surface charge transport, which is perfectly in agreement with kind of the Weber's approach, right? So,
yes,
right. I think it's an open field. We would encourage, people to contribute as much as they can, either experimentally or theoretically, right? It's very, very. I would say very few people are busy in this field, and it would really, to my opinion, the possibilities are gigantic. What one can do with that, it's opened the new door to new technologies and new sources of energy and so on. So I think it's the right time really to do that. So I want to thank you again, Koen, for very inspiring talk, and
Okay.
Thank you all for watching, and I believe that now is really the time for a little break, right? Good afternoon. So welcome back in the studio. Now is next talk is a pre-recorded talk of William Alec, and he will be speaking about the replication of Tom Burden's scalar wave technology. So enjoy his talk. Thank you.
What here? Okay, my timeline. Okay, back in 1977, while attending IIT in Chicago, it's an engineering school or university, I was given a vision of my future. And in this vision, I was constructing an anti-gravity craft. And it's the most profound, astounding thing I think I ever saw. And it was just amazing. It was a craft, a disc craft. And I constructed this craft. And I had no idea at the time how it worked or exactly what I was doing. But in this vision, there it was. Okay, so let's fast forward here 20 years, 1979. And I went to this conference in 1997. And I attended, the speaker was Tom Bearden, and he was speaking about free energy and anti-gravity. And at the time I said, oh my God, you know, it's starting to come together. And, you know, with this technology. And so Tom was speaking about this free energy and anti-gravity technology, which I thought was rather extraordinary. So I went to the conference and was just completely blown away by it because Tom pointed out a flaw he discovered in electromagnetics. Okay, and we'll get into that flaw here in a moment. So now in 2022, and the present day here, I began lecturing about Tom Bearden's technology and replicating it and showing people, you know, exactly what's going on here. So we'll go on to the next slide here. Now, Tom Bearden is noted for some quotes. And the first quote he mentioned, and this was during a conference, is that all matter is made of trapped electromagnetic energy, which I thought was rather interesting. And the second thing he mentioned was that the dimension of time, that we can't see time, but we know time exists because of spatial displacement. Okay. Next slide. Electric force versus the gravitational force. And I put this slide in here to show people out there the huge difference between the electric force and the gravitational force here. And it's absolutely enormous. Okay, the electric force, when you compare it with gravity, gravity is as we know, is an extremely weak force. And so, and when you contrast that with the electric force, we see that we have this power of 10 to the 42nd power, but it's not zero, okay? I want to emphasize that point. It's not zero. And this is what I caught, this is what I think caught the early mathematicians and the early physicists, was that the electric force is so enormous compared with the gravitational force that, well, we can set it equal to zero. But I think that's where the error occurred in electromagnetics and gravity. That's where the error occurred. Okay, so let's take a deeper look into this. You know, what is the electric field, the magnetic field, and the scalar field, or gravity, okay? And scalar just means that whether it's a mass or time, it's all around. It's all around us. Okay. Whereas the electric and the magnetic field are considered as vectors. Okay. Powerful force vectors. And then when we look at the scalar field as being all around us, that would be considered a longitudinal field. Okay. And it can be either directed towards matter or emitted from matter as a change in time. Okay, I kind of think of gravity and time as almost the same thing. Because when you go into the gravity field, you measure a certain rate of time. But let's say you're sitting in an orbit around the Earth, you know, away from the gravity field, you're going to have a different time. You know, clocks are going to tick at a different rate. Okay. Einstein. Okay, Einstein tried to unify the field, okay, between electromagnetism and gravity, but he failed at it. He couldn't find the connection between the two. And so he spent the rest of his life trying to make this connection with the scalar field. Of course, he failed at it. He couldn't figure it out. And so his unified field theory was, of course, a complete failure. Okay. Modern science discovered this connection, and we call it scalar waves. Okay, and this is what we're working on here: the scalar wave theory and practical applications of this technology, because it's mostly, you know, when you speak to physicists today, they either have one or two that they don't have a clue, or it's mainly theoretical. So if you look at general relativity, for example, I mean, yes, you can apply it, but it's mainly a theoretical equation, but you can't apply it to electromagnetics, as far as I know. So the next slide here, Tom Bearden's scalar waves. Okay, what exactly is he talking about? Well, what Tom spoke about in his lectures was, of course, an anti-gravitational wave, which has the properties of being time reversed and longitudinal. Okay, I want to emphasize that it was time reversed and longitudinal. This is the anti-gravitational effect, and that's what we observe with these devices. So if you take your so-called magical device that really works, you put it on a professor's desk, most likely they're not going to have a clue how this works, because it's not in their mathematics. You know, it's not the way that they were educated. Okay. Next slide. How to produce scalar waves. And of course, a number of researchers out there actually did this, okay, in their technology. And we'll get into that later on in the lecture here, okay? So what we have is a cross product of two electric charges. And these charges are set up to oscillate, okay, to converge and then to diverge. So you have this resonant type action occurring here. And that's where the scalar term appears. And of course, this is what Tom spoke about. And these vectors, okay, for these electric charge must be equal and opposite of each other, okay? And what does that produce? Well, that produces something called a zero vector, okay? Equal and opposite charges set up to oscillate produces what's called a zero vector. And Tom spoke about this as well. The next slide. Okay, two types of scalar waves are produced simultaneously here. Okay, what we see on the oscilloscope is a time-reversed EM transverse wave function. Okay, and that's what we see in our various technologies here. We see this time-reversed electromagnetic transverse wave function. The second scalar wave we see is a time-reversed gravity wave, okay? And in this case, since it's time-reversed, we would call that an anti-gravitational wave. And that's what Tom spoke about as well, okay? Time-reversed gravity, or an anti-gravitational wave, or a longitudinal wave. And that you cannot see on your oscilloscope, but you can measure it, okay? If you hook up your device and put it on a balance beam, you find out that this device loses weight. And one of these devices, built by Floyd Sweet and his device, produced an anti-gravitational wave of up to 90% weight loss in his device, okay? Just by setting up these opposing magnetic fields. And we'll get into that a little later here too as well. So just to recap this slide, I just want to emphasize that Tom spoke about two different types of scalar waves, okay? This time-reversed EM transverse wave and the time-reversed gravity wave. Okay, now this is the mathematics that Tom spoke about. Okay, you'll find this in some of his slides where he details the main issue here, okay, the failure of mainstream science. And this was brought about by Oliver Heaviside, who took the original Maxwell equations, which I believe were like 20 equations written in a quaternion form. And so Oliver decided to simplify these equations. And by simplifying it, he threw out the scalar component. Okay? So what you end up with is this cross product of two electric charges producing a zero vector, okay? And that zero vector is empty, okay? And so this is really the crux of what Tom was speaking about, okay, was his failure in mainstream science. Because if you look at the original Maxwell equations, he has the scalar component built into his equations. So when you look at all the mathematics here and say that with the scalar entity, you're using a sine function, okay? So what you end up is a sine squared term. And that's very important, the sine squared term, because that's what we see on the oscilloscope, is the sine squared term, okay? And then his zero vector becomes what's called a vacuum engine. So the zero vector actually has substance in Maxwell's original equations. And this is where the anti-gravitational longitudinal wave emerges from. So the device, you not only see the scalar wave electromagnetic term, but you also observe a weight loss in the device that's producing the scalar wave. And of course, the device must be operated in resonance to see this phenomena occur. And we'll get into that a little later here too as well. So just to emphasize that the scalar term, the sine squared term, is very important. And that's what you do not have in the vector solution that Oliver Heaviside presented and what we have today. So again, you take your device, you put it on a professor's desk, he's not going to have a clue how this works because the mathematics is not there. It's there in the original equations, but it's not there in any modern mainstream science. Okay, so this is what Oliver Heaviside did. I mean, he simplified Maxwell's equations. He did this back in the 1880s, okay? And a quotation here from Oliver Heaviside is that referring to the scalar component, why he took that out, he says that the mystical side of this equation should be murdered from the theory, okay? Because for all practical purposes, it's zero. And then Tom Bearden came along here and discovered this flaw and says that, well, Oliver Heaviside threw the baby out with the bathwater here. And then my quotation, this is the main reason why we don't have Star Trek today. We should have warp drive. We should have anti-gravity. It's built into the mathematics, but the original mathematics, not in the Oliver Heaviside. It's been thrown out. Next slide. How do you determine resonance in these type of circuits? Okay. Well, it's a capacitor inductor combination here. So if we look at the output of these devices, we see that there's a convergence occurring with the magnetomotive forces. Okay. And this is what's producing the scalar wave in our device. And so at resonance, we have minimum current in our device. It's operating at the minimum current level. And that current could go almost to zero. And this is why your efficiency goes way up in these type of devices, because your minimum operating current at resonance approaches zero. Okay, so when you calculate the efficiency between your input and output, that efficiency can go into the billions if you have your coils configured almost perfectly. And this is what Stanley Myers did in his device, what Floyd Sweeten did in his device. He was able to tune the output coils such that the minimum input current can approach zero. And so your, what we generally call COP, your coefficient of performance for the device, can be in the millions. Your efficiency level could be in the millions. So that means that the limit of 100% efficiency is no longer true in these type of devices. Your efficiency can go way above 100%, okay? All because of this minimum input current approaches zero. All right, so what do these resonators look like? Well, here's an example. This is my split flux, what I call the split flux transformer. And so you have an input and then two output coils. And this is what sets up your convergence in these devices. And so the output is driving a capacitor. And of course, there's going to be a load resistor on the output. So what you end up with is what Tom calls a pumped phase conjugate mirror on this device, or a PCM. And then I ended up filing a patent on this type of device configuration here back in 2020. And Bearden lectured on this subject quite a bit in the 1990s. So again, what we're doing here is setting up a magnetomotive convergence, okay, the zero vector. And that's driving this capacitor and resistive load output of this device. So this is a very typical configuration. And you'll see this configuration on many of these devices, okay, that I'm about to present here. Okay, PCM resonators, what are we talking about here? And he says, okay, well, the output is time reversed, transverse electromagnetic wave. And that's the sine squared term that we see on the output of the device. The output becomes more efficient. When it's time reversed, the output becomes more efficient and efficiencies can exceed 100%, as I mentioned before. You can approach 1,000,000%, okay, with these type of devices. And the device runs cold. They don't run hot. They run cold. And that's how you know you're running this time-reversed situation here. And then the gravitational component that's being emitted from this technology is time-reversed as well, okay? So it's emitting an anti-gravitational effect here from the device. And so the weight can either become negative or less than zero is what you can observe for this, and it becomes anti-gravitational. So it's quite amazing here. So it affects the mass acceleration effect, okay, with this technology. Examples of PCM resonators. You know, my split flux transformer is one example. Nikola Tesla and his magnifying transmitter had the same type of coil configuration. We also see that in Stanley Meyer's water car. And we also see that in metamaterial resonators as well, okay, is that it sets up a convergence of the magnetomotive forces, okay, inside the materials. All right, so here's an example of what I'm talking about here with the split flux transformer. And I do have a patent on this. I received a patent, I believe it was 2018 timeframe. And there's the patent number that's listed here, US patent. I filed it back in 2015, and then I finally received the patent a few years later. It's for an energy management system. And so what you see in this configuration of this transformer is that we have the AC input, okay, which is inputting your source current and source voltage, and the output drives a capacitor and resistor. And that's what we measure on our outputs here. So we're driving a real load with the capacitor, and then we see the coil arrangements, which sets up the convergence. And the convergence is very important because that's what you see in all these devices, okay? So what is behind this PCM resonator? And this was a diagram that Tom Bearden put up during his lecture, but his diagram didn't really show a lot of detail. It was mainly focused on what is known in science, in optics. You know, this is really an optical effect, but here we are running at a very low frequency, okay? We're not running at optical levels here. And so Tom didn't present all this detail that I'm providing to you today, okay? And so on the left side here, with waveform 3 and 4, is that you see the time-reversed scalar wave component, okay, the transverse wave function. And it's time-reversed, meaning that the wave is moving backwards in time, okay? And that's really the product of what we see here with wave 1 and wave 2, okay, are pump waves. And so the pump wave is producing wave 3, okay? That's our input into this device. And then we see a magnified output, which is wave 4, okay? Now also what's occurring here is that the device is producing this time-reversed longitudinal output as well, okay? This is our second scalar component that I spoke about earlier, that W5. And this is what's going on in these type of devices, is that they lose weight as well. So if you took this device, you put it on a balance beam, you'll see that the balance beam will move. The device will get lighter, okay, because it's operating in this time reversed fashion. And this is really set up with two converging electromagnetic waves, okay? And so this is some of the mathematics here. W5 is, of course, a change in time, okay, which is anti-gravitic in this case. Okay, the next slide. PCM resonators, the output wave function. And so this is what we see here. The input wave function, W3, is your sine squared, and that's your pump waves, okay? And then they produce this magnified W4 term here, which is your output sine squared term. Okay, this is your outputs. This is what you see on oscilloscopes. Okay, this is for real. Okay, there's nothing here that's really made up. I mean, these technologies have been measured, and so this is for real. And so you see this time reversed output on the sine squared term here. Okay, so well, let's go back in history here. What exactly did Nikola Tesla do to make his magnifying generator? Well, he sets up this magnetic motive convergence, okay, with two coils, and his two coils are labeled M on his patent. So you can look up his patent and then see that he has two coils, two output coils, two capacitors, and a transformer coil arrangement here. And of course, he filed this back in 1896. So he's been doing scalar projects for a very long time here. Okay, but nobody understands it. No one, a physicist, you put this on a physicist's desk, he's going to look at it and says, well, we're going to change things around a little bit, put one coil. He's really talking about one coil arrangement, one capacitor operating as a resonator. No, that's not what Tesla was doing. Okay, he's setting up his convergence. Okay, so this is what Tesla was doing, okay, to get his convergence going here. He's got his generator, his two coils labeled M, and he's setting up his magnetomotive convergence here. And it's set up as mu times H, okay? And so that produces an output voltage, okay, with minimum current driving his transformers, okay? Now let's look at another device here. Another inventor came along, 1992, by the name of Stanley Meyer. He's on the internet. I believe his patent is also on the internet as well. You can download his entire patent. And this has been replicated and tested by another inventor. And he presented his information at the Tesla Tech conference a number of years ago, 5 or 6 years ago. And he replicated all of Stanley Meyer's equipment here, and he observed an efficiency because Stanley was able to tune his coils. Okay, he was able to tune his coils. He observed an efficiency of about 1,200%. Okay, and that's what was driving his output. His output is, you'll see number 71 and 61, and that drove a water, what Stanley called a water capacitor. Okay, and all that this water capacitor is just a couple of plates and water that he used, distilled water in his capacitor. Okay, so his dielectric in this case is going to be water. And so Stanley was producing a water fuel from this. Now, who was doing this before Stanley? Another inventor that goes by the name Yule Brown. Okay, and you can look him up as well. Yule Brown was producing what's called Brown's gas. And what is Brown's gas? It's a hydrogen-oxygen combination. Okay, normally when you disassociate water, you break it up into separate containers here of hydrogen and oxygen. Okay, but that's not what Stanley was doing here, and Yule Brown wasn't doing this either. Okay, he was doing this as well, setting up his water capacitor, and he was producing this gas called HHO. Okay, HHO, and we'll get into that a little later here as well. So this is what Stanley was doing. Okay, this is his device. I put the dots and the arrows here to show you how things are converging. He's setting up his resonant charge, what Stanley called his resonant charging chokes, okay, on his output transformer. So he had an input side here feeding these two resonant charging chokes, okay, and that's what drove his water capacitor. Okay, so what is this water fuel that Yule Brown produced, as well as Stanley Myers in his water car? Okay, because what Stanley did is that he took this apparatus and put it into a dune buggy, and you see that on the internet as well. And he ran his dune buggy on this water. Okay, so what is this? Well, it's known as hydroxy gas. That's what researchers call this. It's a special gas that's a combination of HHO, okay? And a researcher a few years ago gave a very nice talk about this. It's electrically expanded water, okay? Electrically expanded water. And it's highly flammable, okay? So this gas, it's a highly flammable mixture. And again, I want to emphasize that we're not separating hydrogen and water into two different tanks. It's combined as one. And so when you burn this gas, it burns cold. It doesn't burn hot. This gas burns cold. So it burns at a temperature of 266 degrees Fahrenheit, or 130 degrees Celsius, okay? So this gas burns cold. But here's the amazing thing about it. It can vaporize tungsten, and tungsten won't melt until you reach about 10,000 degrees Fahrenheit, okay? But it can vaporize tungsten. Well, how can it do that? How can this gas burning cold, okay, vaporize tungsten? Well, it's electric. It's an electric flame, is what that is. Okay, so you're made. So we have a multi-plate electrolyzer and a DC voltage and current, and that's exactly what Stanley was doing. Okay, and so the objective here. Well, what's the objective of all this? Well, burn water, not gasoline. Okay. Burn water, not gasoline. And so Maury King came along. You can get his book, The Key to New Energy, okay? And there's the ISBN number. You can get his book where he talks all about this water fuel, okay? All these characteristics behind this technology, okay? So we don't have to burn these hydrocarbons. We don't have to do this. We could just burn water instead. Run our engines on water. So what is this water fuel? How do you make it? Well, I bought one of these devices. Okay, you can see the plates here, a power supply. Now, the problem with this particular setup is that it's not efficient. Okay, it takes a lot of power to make this gas. And that's where the scalar energy technology comes into play, because you can replace that power supply that you see on on this slide here with a scalar energy generator, which is using either my transformer or these coils set up in this converging method like Stanley Myers did, or you can use a Tesla coil arrangement, okay, to make this gas. And what you do is that you pour your fluid, okay, you can use distilled water, okay, with the scalar energy, and fill up this tank and then make this gas with it, okay? So you can actually buy this, this water torch, okay? It's available online that makes this HHO. And the issue with this is that it's not energy efficient, okay? And you have to use a potassium hydroxide added to the water as a catalyst, okay? But Stanley mentioned that you don't have to use this catalyst. If you use scalar technology, okay, with this, replace that DC power supply with your scalar power supply and produce the gas that way, you don't have to use a catalyst at all. You can use straight distilled water with this, okay? And so your output is what? Water vapor, right? When you burn that gas, hydroxy gas, your waste product is water, which I think is quite fascinating. Okay, so this video, I highly recommend people to watch this video because it goes into quite a bit of background here on relativistic quantum field theory. And so when I saw this video, towards the end of it, I'm looking at it and I say, well, there's the scalar term, the F minimum. See, to produce particles with mass. Okay, you have two types of particles here. You have particles with mass and particles with no mass. You know, for example, a massless particle might be a photon or something, okay, on that order. There's no mass associated with that. But yet, with particles like an electron, real matter, okay, has this output, and I looked at that and I says, oh my God, that's a scalar term, okay, that's really producing a scalar wave. And so that's what mass does. It produces a scalar wave, which in turn produces a gravitational wave. A longitudinal wave comes out of this. And so it fits in what Tom Bearden spoke about back then, that matter is made of trapped electromagnetic energy, okay? And so what you have are like two photons rotating, trapped, and producing the scalar wave component. And that's what gives you gravity, okay? A very weak force. It's very weak, but it's not zero, okay? I just want to emphasize that it's not zero. Okay, so this is my test bench. This is a scalar wave test bench. And it shows an oscilloscope, a power supply, my transformer, driving the resonator here, which is a capacitor and a load output, and some meters hooked up to it to measure the current and the voltage. And so I wrote some software that does all these calculations, okay, that determines what is my efficiency of this device, okay? And so with this power supply, it just generates my AC form, my sine wave, driving a transformer, because you can only power transformers in this case from an oscillating source, whether it's AC or a DC source. It could be, it has to be pulsed, okay, which of course is what Stanley Myers was doing here with this rectifier in his transformer arrangement. Okay, so you have this pulsed output, oscillating output, and so I wrote this software that reads the voltages and currents going into it, coming out of it, looking at the scalar wave component on this oscilloscope. And you see the actual scalar wave, the sine squared term, is the top trace. And that top trace is added to the sines, to the input sine current. Okay, so it's sines plus the sine squared term. And that's why you see this kind of funny looking shape at the top. And I'll go into a little detail in a few other slides here with that. So this is the real thing producing the real sine squared term. Okay, and that's what gets added into the waveform. Okay, so what are these waveforms? So I did some MathCAD waveform calculations. You know, I set this up in MathCAD, put my equations in, and so I see what the input waveform is. Okay, that's my sine wave input. And the scalar waveform on the output, okay, is up there at the top. That's my sine squared term. And so when these two waves are added, which is what you see that kind of funny shape there at the bottom, the summation of the input and scalar waveforms. This is what you actually see on your scope. And so to go back a slide, okay, there's your oscilloscope, and that's that funny wave shape there at the top, that blue wave shape. Okay, so this is what happens when you add these two together. And so the actual scope is what we see, okay? This is input waveform, the sine wave, plus the sine squared term, okay? And that's our scalar wave. And so this is an actual scope reading. So what are we doing here? Okay, to determine transformer efficiency using AC circuit analysis, this is what we're actually doing. So we have our AC waveform on the input, and we're looking at voltage and input current. On the output, we're seeing our output current and our load. And so the device under test is our PCM. And that's where we have our coil capacitor arrangement, okay? And so how do we measure AC circuit analysis? Well, we look at these various values here, and then we look at the phase shift, okay? The apparent power versus the real power, and that's where we see the reactive power, okay, on our technology. So this is just plugging in some test values here, and this is what we see, power input and power output, okay? And then from that, we can determine the efficiency. And this is what my software does. It does all these calculations here. Okay, so the next slide. This is my software. This is written in Visual Basic, actually. Visual Basic is actually a very solid platform to write this software. And so it reads the scope, sends messages back and forth to the scope, and takes all these readings on the input and output and does these calculations of of computing the efficiency and input phase angles and output phase angles. So it's doing all this number crunching, okay? And then we see on the output of this thing is that, oh boy, 90% efficient. And usually transformers are right around 80%. So we're seeing an increase in efficiency on this output here. So that's how we know that the output of this device is that it's time reversed. There's some time reversal going on here, okay? And so what is my software doing here? Well, it's doing all these calculations, okay? So it's looking at phase angles, apparent power, reactive power, taking the arc cosine, and doing all this number crunching, okay? Now, this software is actually available to be downloaded for free, okay? It's on my website. And it works with this particular type of scope that we have, that I use. It's a Tektronix 2024B scope. And I think they're actually, they're still available, I think from Newark Electronics would be the supplier on that. And so I captured all these screens from the transformer here. And it's doing all these number crunching algorithms here. So I'm able to capture these screens and then load them onto the clipboard and make up these slides here. Okay, so Tom Bearden's applications for this device. And Tom spoke about scalar wave interferometry, okay? Tom wanted to get a big DARPA military contract. So he never really went into a whole lot of detail on his device, what he was actually doing, but he did present a lot of this data, okay? And so I had to spend a lot of time putting all this together, all right? Putting all this together because Tom wanted a big DARPA contract, okay, to do scalar wave interferometry. And what is scalar wave interferometry? Well, it's a defense application. It requires two ground-based scalar wave emitters, okay? And these two emitters, where the beams cross, is your target. Now, it could be an airplane, a satellite, whatever, okay? But where these beams cross, create a strong electromagnetic field, okay? And it can destroy electronics in your target zone. So the next slide here, scalar wave interferometry. I did a lot of mathematical analysis with scalar waves. And I noticed that, you can create an electromagnetic virtual ground where these beams cross. Wow, that's cool. And then when you look over to the right side of this, if you phase adjust your scalar wave terms here, you just shift them, okay? It says, you can create a strong AC potential, okay? Right there in space. So you can short out anything, okay? Anything that's there. You can short it right out. Because in that region of space is creating a strong electromagnetic AC potential. Wow. So this is what Tom was speaking about in the conference, okay? And so scalar wave interferometry, okay? You have your two scalar wave emitters, okay? And that's where you can create either a virtual ground or a strong AC potential, okay? So these are all visuals here. Tom did show something like this in his lectures, okay? He did speak about these interference patterns, okay, of scalar wave interferometry. Okay, so this brings about brings up another researcher that I ran across back around a while ago. I would say about a good 10 years ago or so. A researcher by the name of David Sereda made a movie. And in this movie, he interviewed this researcher, this developer at Lockheed Skunk Works, I believe. I believe it's Skunk Works. Boyd Bushman is a weapons developer. And he did this experiment. And he spoke to David about it, giving him all the details of this experiment. And you can actually replicate this experiment, and I'm going to present all this data here that I have of what Boyd did, what Boyd Bushman did. And what he did was that he took two magnets, which is really our technology, okay, because we set up these converging magnetomotive forces, which are really two magnets, and you force them together. And when you take these magnets and you force them together, it decreases the mass acceleration effect, okay? It generates a time-reversed effect here, and it's anti-gravitational, okay? Basically the same thing what we're doing in our technology, Boyd is doing with actual magnets. And you can do this. You can do this experiment. So what did he do? Well, this is the experiment that I did. I conducted this back in 2009. It's called the Boyd Bushman drop test experiment, where you take these magnets, you kind of wrap them up to look like a rock, and you drop them, okay? And then you observe the test rock with an increased mass acceleration effect, okay, with the test rock, with your test rock. And so here we have it. You know, this is how you make the device. Okay, you have two neodymium magnets. And what you do is you set up this jig here to force them together. And you actually epoxy them. You can use JB Weld epoxy on these magnets. Okay. And there's the jig there, forcing the magnets together. And there's the magnet assembly. You notice in this case here, the north-north configuration is together. And it doesn't really matter. It could be south-south or north-north, this configuration here. And there's your magnet assembly, showing them epoxied together. There's an ordinary rock. There's lots of rocks there in Arizona where I did this test. And then you take the rock, you just wrap it up with some electrical tape here and a nice bright blue rock here, and then some red electrical tape, for example, on the right. And then what I did was extend Boyd Bushman's experiment using magnets in a attractive configuration. Okay, and I compared that as well. So that when I did the experiment here, comparing the rock dropped with the rocks with the opposing configuration, the opposing configuration fell slower, replicating Boyd Bushman's experiment, because he did this at Lockheed, okay, and I observed the same effect, okay, the same effect, and you can replicate this as well, and I videotaped it, okay, and you can actually see the rocks with the opposing configuration fall slower, but the rock with the magnets in the attractive configuration fell faster. I said, aha, that's interesting, very interesting. Because when you show these rocks in the attractive configuration and the opposing configuration, guess what? You can build a warp drive with this, okay? Because magnets they bend space-time. They not only produce their magnetic field, but they also bend space-time, so you can build an Alcubierre warp drive using these magnets, okay, and these various configurations. And this is how you do it, okay? And so I came up with what's called the ABBA warp drive engine propulsion technology, okay, where you see magnets in the attractive configuration and then magnets in the opposing configuration, and you spin them. And when you spin them, you get something called the Barnett effect, okay? And then when you spin them in counter-rotating fashion here, you can get a counter-rotating setup here that eliminates what's called the P factor. And that's what you observed in engines, okay, plane engines, is that you have to rotate these propellers in opposing configuration to keep them from spinning the whole craft. So that's where this dual nacelle configuration comes into play, okay? Because you have magnets spinning in there, and you must spin in such a configuration where it counters the P factor effect, okay? So you can look this up as well. So this is how you build a warp drive engine, okay? And it's called the Alec Bushman Alcubierre warp drive engine. So it's just a silly little name I came up with there, okay? So I'm not opposed to gravity, okay? But our technology is. So this is a cute little t-shirt I came up with. And this is my business card with my email address and website. So you can check out the website, goes into a lot more detail. You can look at it, ponder it. This technology, see how you can replicate some of this. Okay.
Thank you, Bill.
And these are all my references. Right here. And so that's my presentation.
Great.
So
Thank you, Bill.
Okay, very good.
Thank you, Bill, again. So it was
questions.
a very interesting presentation, and now is the time for question and answers. So can you hear me right?
Yes, yes, I
Very
can.
good.
Can you hear me okay?
Right, so can you elaborate more
hear
on
me?
the phase conjugate mirror, PCM, right? Can you explain a little bit more clearly what do you mean with this PCM? What does it mean? Phase conjugate mirror. I believe there is a problem with the connection, probably, right? I apologize. Seems to be that we have some technical problems, right? Ah, very good.
Okay. Can you hear me okay?
Bill, can you hear me?
Yes.
Right. So shall I repeat the question?
Yes.
Yeah, the first question was whether you can elaborate a little bit more on the phase conjugate mirror. What does that mean?
Uh-huh. Well, what you do is you set up two electromagnetic pump waves and you pump your material, okay, with this. And the material here is, of course, this iron, okay, the transformer iron material. And you pump that just by using opposing magnetic fields. And so the magnetomotive force is what we're working with here. And when that's set up in an opposing configuration, okay, creates this what's called a phase conjugate mirror. And that's what Tom Bearden called it in his lectures, okay? And what that phase conjugate mirror does is that it sets up a time reversed output, okay? And that's what we use to drive our technology with. And so on our output, we see this phase conjugation occurring, which is a time reversed wave, or the sine squared term becomes time reversed. Okay? And that phenomena actually happens. I mean, I see it on our output, on our device, and what it does is that it decreases the input current requirement on this device. And that's why I show this kind of a reverse profile on our input current. Okay, because it actually decreases when you reach the resonance on your output capacitor and your output of this transformer arrangement. Okay, you see this dip in your current input. And so when you do the power calculations, you find out, lo and behold, your efficiency starts to go way up. Okay. Now on my transformer, the coils are not tuned. Okay. They're just straight opposing coil configurations. When you look at Stanley Myers, he was able to tune his output coils and match them as close as possible. And that's what you want to do, is to match the output coils such that you get as much cancellation as possible. And when you do that, your input and output, when you do the efficiency calculations, go way up. Okay? And it can easily exceed 100%. Now with mine, split flux transformer, the coils were not tuned. They were just straight coils. And I observed an increase in efficiency. And my increase in efficiency was able to go up to 90% efficient, when typically a transformer input-output coil arrangement, your efficiencies are right around 75, 80% efficiency. So I observed an increase in my efficiency output. Now, if I was able to balance those coils properly, okay, I could have that efficiency very easily go way over 100%. And that's what was observed in a number of these technologies that use this opposing coil arrangement. For example, Stanley Myers and his water car. You observe like 1,200% efficiency with this tuned coil arrangements. And Floyd Sweet, with his device, observed something like a 10 million% efficiency. So that means his input current was rapidly approaching zero. Okay, and he was producing that scalar wave output. And so this is what you want to do, is to be able to tune those coils, okay, increase your efficiency.
Very good. So do we have some other question to Bill? Right. So there is a new question, right? What is the effect of PCM on split flux transformer performance exactly? I think that's what you probably already explained, right?
Yeah, yes, that's what I was showing in the slide, is that right around 90%, and the coils are not tuned.
Right.
Okay.
Very good. So, thank you very much for this inspiring presentation. I wonder if you have a detailed description in order to replicate the over-unity burning of water. That's probably a question related to Stanley Meyer, right?
Right, yeah. Max Miller, okay, was a presenter at Tesla Tech conference about 4 or 5 years ago. And he gave an excellent presentation replicating Stanley Meyer's water car. I mean, he replicated all the circuit boards and his transformer, and it was highly efficient. He was able to tune his transformer, and he did an excellent job with that replication. And he was able to hook up his transformer to these water capacitors producing Brown's gas. Okay, and that's what you want to do here, is use scalar energy, okay, for producing this hydroxy gas, and that's what you want to run engines with. And then some researchers in Phoenix, they didn't replicate anything what Stanley was doing or any of these scalar technologies, but they were just using a straight power supply, which of course uses a lot of power to make the hydroxy gas. And they observed in their engines, okay, because you feed this as you replace your air input on a gasoline engine, okay, you place it with a hose feeding this hydroxy gas right into your air intake, okay, on these gasoline engines. And they observed very high efficiency, okay, of burning this hydroxy gas, okay, in their gasoline engines. So it drastically reduces any sort of pollutants, okay, associated with burning hydrocarbons. So that would be the way to go with this. I mean, they were using a full engine, a gasoline engine, to do all this testing with.
Thank you. So, Dr. Alec, thank you for your excellent presentation. As far as I can recall, at several occasions, Dr. Tom Burden refers to Tesla electromagnetic theory as a cold electromagnetics. Would you mind to clarify what is cold electromagnetic force that he meant to refer to Tesla work?
Well, this is where the PCM comes into play, and producing this time reversed wave. And we see that electromagnetically, okay, as a scalar wave output. That's your sine squared term. And then we also see that with the anti-gravitational component as well. Okay, that's producing this wave number 5 on the PC. If you look at the PCM diagram here, the 5th wave is being emitted by the device itself. And so what Tom referred to is that it's all coming from the zero vector. Okay, when you do the calculations with the Oliver Heaviside electromagnetics, the zero vector is empty. Okay, but when you look at the original James Maxwell's equations, they include the scalar component, and your zero vector is not empty. It contains this what Tom calls a vacuum engine, And this vacuum engine is what's doing all this magic, okay, of producing this time reversed scalar EM wave and this time reversed gravitational wave as well, okay? And this is what we want to use in our technology, is this scalar wave technology to improve the efficiency of our machines.
Mhm.
So
Thank you.
this cold EMF, that's all part of this PCM that Tom was speaking about.
And there is one more question. And secondly, what kind of equations referring to those Tesla experiments? Question mark. Thank you.
Okay, now I really don't know much about what Tesla was doing um, with any of his equations. He just spoke about the effects, some of the effects that he observed, and um, it's my opinion that Tesla was using the scalar wave technology, because it's just how he described some of these effects. For example, some of his waves he mentioned move faster than the speed of light. Okay, and we're all doing that with canceling out the magnetic component in these waves. That maybe it reduces or eliminates the speed of light barrier, okay, in electromagnetics. Because that's what we're really stuck with, is that when you work with Oliver Heaviside's equations, you're stuck with the speed of light. And I think when we look at Tesla and what he described, and when we start looking at Tom Bearden's technology as well, you start to overcome these limitations, and it's exactly what they did when they conquered the speed of sound, right, with their aircraft.
Right, Bill, there is another question. Can you please explain in more detail how the Floyd Sweet device and your further development produce anti-gravity?
Okay, Floyd Sweet, very interesting character. He lived in California. I think it's Rex Research still carries Floyd Sweet's technology. I did a presentation on Floyd Sweet about 4 or 5 years ago. Okay. And I'm working with some of his schematics where he's got two opposing coils creating the scalar wave phenomena. Okay. And Tom Bearden spoke about the Floyd. He actually saw Floyd's device. He was able to witness Floyd Sweet's device in person, okay, watching it operate. And Tom was saying that the device lost like 90% of its weight, produced like 10 million% efficiency. He had near zero input current on his device. And when you look at it, it looks conventional, okay, except that the two coils are set up in this opposing configuration. There are photos of Floyd's device out there on the internet. I presented a few of those photos in my lecture, okay, that I gave at Tesla Tech, okay, on Floyd Sweet's device. And so you see this 90% weight loss in his device. Now, another researcher by the name of John Hutchison, perhaps many of you heard of John Hutchison, was able to levitate a 90-pound bowling ball or cannonball, okay, with this technology. And you see all this stuff flying around in his lab when they exposed with these converging Tesla, he was producing all these Tesla beams or radio wave signals in his apparatus. And another device that comes to mind is the German Nazi Bell device. I don't know if many of you have heard of that. It's out there on the internet, where they set up converging spinning magnetic fields called the Glocke, I believe is how you pronounce the Bell device that the Germans built during World War II. And that device was actually tested in Poland. Poland at a concentration camp is where they set up that test apparatus. And there was a fellow by the name of I forget his name, but he spoke about the machines of the Wunderwaffe. Okay, and I think that book is still available, but you need the original print. Okay, if you're going to look at the original description of the Glocke, that's what you need to look at, because they set up these counter-rotating fields, okay, in this device that's bell-shaped, and they use DC current, okay, and that's very important, is that you have to use a DC opposing magnetic flux, and then you spin these, you counter-rotate these spinning magnetic fields to get that cancellation effect going on. So that's what all these devices are using, is a canceled magnetic field, okay, to produce this anti-gravitational effect.
Ian mentioned that.
Okay, another question here. Any?
Right.
Okay, now personally, I have not observed anything over 100% in my technology, and that's because the coils are not tuned, okay, in my device, and I'm still working on that part of it. This last year here, I've been spending a lot of time writing the software to do all these calculations, okay? But there's a next phase to this that I definitely want to get into with the scalar technology. And that's a form of scalar interferometry, okay? Not to transmit, okay, but to produce on the test bench. And so my next phase of operation here, okay, is to produce this interferometry test system that I want to work on, and that's what I want to produce a real AC wave with, okay, this high potential. And so my next phase is working with that technology.
Very good. Are there any other questions? Right. So, Bill, do you see the question, right?
Yes.
Can you share some values
okay,
to
the
the
drop
extended
test.
Bushman drop test experiments, right?
I have some videos that I took a number of years ago on this drop test. And what Boyd Bushman spoke about, you know, in David Sereta's video, is that he described quite thoroughly, you know, his opposing magnet test when he dropped these magnets down an elevator shaft over at Lockheed. Now, I do know that Lockheed extended, built some machinery, okay, to further develop Boyd Bushman's concept here. And I think he's got some patents out there. Boyd has some patents out there as well. But what you want to replicate, and this is what other researchers have done as well, is to replicate Boyd Bushman's original drop test. And I extended it using magnets in just the opposing configuration. Of course, they come together. Okay, the magnets, neodymium magnets, and it's exactly how I described that. They are quite dangerous to work with. Okay, and I kind of wrapped them up with some electrical tape. And then what's interesting about this is that they dilate time, okay, with this technology. And, I did a number of experiments at a place called the Mystery Spot, okay? I even developed mathematics. I call it natural relativity. Einstein calls it his general relativity, working with tensor type physics. Me, I just work with regular exponential functions, okay, and I call it natural relativity. But I came up with something that converts time, okay, which to me is what gravity is. It's the tick rate on your clock that changes. Now that tick rate can either increase or decrease, depending upon how the curvature is occurring. And so if the tick rate is increasing, that's your anti-gravitational effect. Okay, it's blue shifting. But if it starts to slow down, that's your red shift. Okay. Now, what's so interesting? You could put this you could put all this to the test. Okay, you can test it, and the place to test it is a place called the Mystery Spot in Santa Cruz. And there's a number of these mystery spots along the coast, along the West Coast. Now, why this phenomena occurring is a mystery, and that's why they call it the Mystery Spot. Okay, you can look this up on the internet. This place is in Santa Cruz. You can go there and test it, and what you observe is something called the shrink-grow phenomena. Okay, where people, they change positions, and their height, they either grow in height or they shrink in height. And you can actually see this phenomena occurring. Okay? You can see it. It's demonstratable. And then I developed some technology that measures that phenomena. And a lot of psychologists want to write it off, as an illusion. It's not an illusion, this phenomena. This phenomena is not an illusion. Okay, it's for real. And you can measure that phenomena, but how do you measure the shrinking phenomena or growing phenomena? How do you measure that? Well, you can't use a yardstick to measure that, because your yardstick is going to shrink or grow with you. So the only way to measure that phenomena is with time. Okay? You look at the dilation effect. And of course, when something grows, that indicates a blue shift. If it shrinks, that's your red shift. Okay? And you can actually see that in time, that shifting phenomena. Okay? And so you look at the shift and you feed it into my gravity equations, and lo and behold, okay, you find out what your shrink-grow phenomena is. Okay? I know it sounds crazy, but it's for real. Okay? And this is what you use to measure gravity, is time dilation. Okay? So
very good.
that's
So,
my presentation.
Thank you for your questions and thank you for your answers, Bill. So it was excellent. Thank you a lot, and I hope to see you soon.
Yes. Carry on.
Okay, and now is the time for the last presentation, which will be done by me again, right? And it's about the Tesla magnifying transmitter experiment we are doing here in Czech, right, in Prague. Very well. So, good. So that's my first slide. I must say that these kind of experiments which we are doing now, and I will present them, are relatively new. So I believe that in a couple of weeks or so we will have more and more kind of results. The number of interesting results is growing. So if we can go to next slide. First of all, I will present what is our inspiration. So I think the biggest inspiration, of course, is Nikola Tesla, who is a main kind of who triggered all this research. And I found a couple of people from a kind of recent time which are very, knowledgeable about what Tesla was doing. For example, Peter Lindemann books The Free Energy Secret of Cold Electricity. I really recommend this book. It's very nice and inspiring. Then Secret of Cold War Technology by Jerry Vasilatos is amazing book. Actually, I was so impressed by this book that I wanted to translate that into to Czech language. And what I found is something which is really characteristic for this Tesla research, because a lot of people are speaking about Tesla, right, these days, but not really everybody has proper knowledge, I would say, and understand what Tesla was doing. I myself also, I think that it's much more important kind of to look at Tesla papers and patents with right knowledge, such that you can really acknowledge what the Tesla research means, right? There was one sentence also, or one comment in the book, and he said, look at the mainstream media to see how they treat Nikola Tesla these days. And then I Google and ask, some paper or article about Nikola Tesla. You can also do it, and you will find really very funny kind of papers related to that Tesla, okay, he was kind of, right, he was brilliant scientist, but he really didn't discover many things, alternating current and so on. But, a very strange kind of statement about Tesla these days. But I think, to my opinion, Tesla was probably the most brilliant scientist all ages and so on. I really have a hard time to understand everything what he has done, and to my opinion, we are now at the very beginning, and we are kind of scratching the tip of the iceberg with those experiments we are doing now. So there is much more yet to be discovered, right? Then another inspirational guy is Eric Dollard. I read some of his books where he is kind of trying to explain which kind of mathematics Tesla was using for his kind of research in polyphase and so on. And to my opinion, it is very closely related to quaternion algebra, which has been discussed this morning. The hyper-complex numbers and so on. But, right, so Eric Dollard is one of the kind of, some people consider him as a living Tesla these days. And many inspirations I found also in videos of Adrian Marsh. And he has the link to his web page where he is presenting a lot of discoveries and interesting things. I even didn't have the time to went through all of this. There's really a lot of material, very interesting material about that. So majority of what we are doing was inspired by Adrian Marsh, right? Very good. So we can go to next slide. So what I'm going to present now, it's, I think it's related also to motto we have in our laboratory, which says, say what you do and do what you say. I think I like this, and I don't want to spend too much time to explain, but I hope you also understand what I mean by that, right? So if we can go to next slide, right? We are speaking here about the electric power system in 21st century, right? And I like actually the quotation of Albert Einstein, who say, no problem can be solved from the same level of consciousness that created it, right? I think that's very deep idea, that if you want to solve a problem, you really have to step up from the level of the consciousness where the problem arose, right? So, to my opinion, majority of known kind of, I put in the quotation mark, free energy technologies reflect principles discovered already by Nikola Tesla. Why I put the free energy device in quotation mark is because there is a lot of confusion, to my opinion, ongoing confusion related to what the free energy is. As we said in my previous presentation, that the solar panels are also the free energy devices in a way that the COP, they are over unity devices and so on. So I believe that there is a possibility, or there are many possibilities to explore also different mechanisms than the solar energy or wind energy and so on, where we can kind of explore also the principle of quantum mechanics, zero-point energy, and so on. In order to make a progress in the electric power system towards the kind of future, I believe we need to re-examine concept of space-time continuum. I already discussed that. Gauge freedom, to my opinion, very important kind of misleading situation in concurrent understanding of the QED and the classical electromagnetism that we have, we are using the, so to speak, free gauging of the vector and scalar potential in a way that we believe that these potentials are pure mathematical construction. However, the quantum mechanics, Ahamorov-Bohm effect, and so on show us that this potential might be as real as the electric and magnetic fields. And to my opinion, we have also to re-examine the concept of ether, right? We also discussed the Michelson-Morley null experiment, but it doesn't really necessarily mean that the concept of ether should be rejected forever. As already mentioned, that also Einstein admitted this idea. So can we go to next slide? Few bold statements, right? Electromagnetic phenomena in the field of high voltage and high frequencies are key to understanding this new physics. I think in the region of high voltage and high frequency, there are really many of the new phenomena which is difficult, or to my opinion impossible, to accommodate into the concurrent classical electromagnetic theory. So there are yet unrecognized physical field which Tesla called radiant, or nowadays we call it scalar, etc. Then there is also a phenomenon related to, if you measure the VI characteristic in high voltage discharges, then you see that the VI characteristic shows something what we call the negative resistor. There is a lot of ideas going in towards the, as discussed already, the power transmission, Zenek waves, and so on, single wire electric power transmission. Then we have discussed a lot of today about this observation of superluminous phenomena, Coulomb wave, etc. Then, as we learn from Professor Assis, the Weber electrodynamics maybe also allows us at some point to understand the universe is actually electric, right? So that's the notion. I think there exists a huge community of people who are really working on the electric universe theory, right? It will allow us, to my opinion, also to understand more clearly what gravity is. And we also see in this region a new type of phenomena like cold electricity, etc. You know, I will show you later, you know, these effects are, I think there are so many strange effects which we have no clue yet what it really means. So if we go to next slide, Kuhn van Vlaanderen already mentioned here this example of the Russian group, Russian team, Strebkov, who they have published, or somehow you can find the paper with the title of Single Wire Electric Power System for Renewable-Based Electric Grid, right? So the paper is from 2000. I think there are also some newer version. The idea is here that you use something like a Tesla transmitter to generate very high tension and high frequency field, and this kind of electricity can be transported over the thin wire to the receiver, where in the receiver stage could be either some some system like a Gratz bridge, or you can use a step down Tesla transformer again. And the resonance mode of oscillation with frequency about 30 kilohertz was used to provide the most efficient power transmission. It was experimentally proven that this SWEPS has quasi superconductivity properties. I just pick up a couple of sentences from this paper because I think it's really opening a very interesting new era for the research, right? So the next slide. Yeah, I'm speaking about this Tesla magnifying transmitter. So I put some, complicated, for simple words for layman. What the Tesla actually, what the transmitter, what it does, right? So Tesla use an inter-resonant interaction between two resonance circuits. I call it sometimes also meta-resonance interaction. The resonance, I think everybody knows that if you have a pendulum, right? So in order to keep the pendulum running, you have to push it in the resonance way, right? So you cannot push it arbitrarily, so that's the meaning of resonance, right? But if you, maybe not so well known is that if you have two pendula, kind of, coupled pendula, then if they are in the resonant mode, it means that they have the same properties, right? Then, and you let one swing, for example, the red one, then you will realize that after a while, the energy from the red pendulum is transferred fully to the blue pendulum, so the oscillation in the red pendulum will almost cease, and you see the maximum on the blue pendulum, and then the energy is returning back to the red, and so on and so forth. So that's also the basic idea between the Tesla magnifying transmitter, that you have two electrical pendula, let's say two electrical resonance circuits, LC, L1C1 and L2C2. And if you bring the one resonance circuit into an action, so it starts to resonate and it transfers the full energy into the other resonance circuit and back and forth. This process is time to time also called a beating, right? If we go to the next slide, please. Right, so that's kind of very schematically the full kind of design of the Tesla magnifying transmitter. So you usually have a transformer, the high voltage transformer, 10 to 50 kilovolts, for example. And then here you have a primary circuit, which is closed by so-called sparking gap. The idea is that whenever the transformer will start to charge the capacitor here, that at the moment the capacitor reach the high voltage, right, then the sparking gaps get shorted, and there will it will form the separated kind of primary LC resonating circuit. There is also the secondary coil, which has many more turns and higher high L, the higher inductivity. The coil has inductance, right? The high inductance, and but there is no C, and there is no capacitor, but the capacitor is kind of parasitic in this case, right? Because there is interwinding capacity and so on. So if we go to next slide, please, then at the moment the sparking gaps kind of get shortened, then you have isolated LC circuit, we call this primary LC resonance circuit, with the primary resonant frequency, right? So this is typically tuned by the value of the capacitor and the coil. And if the secondary coil is tuned to the same frequency or similar frequency, then the energy stored in this system, which is typically a couple of even joules, is transferred to the secondary circuit and back and forth, right? And but if usually if the energy is transferred to the secondary circuit, then there is a kind of electrode high voltage end of the Tesla transformer, and usually what happens is that the high voltage, the huge tension on the hot end of the Tesla transformer will break through the air, and you will observe the discharge, and the energy is kind of wasted in the discharge. But if not, then you usually see this kind of beating between the primary and secondary circuits. Very good. So we can go to next slide, I believe. Right. So this is a picture of one of our, that's version number 16 or so, Tesla transformer we built in our laboratory. So here you see a kind of this high voltage transformer, which is made of three these are microwave oven transformers. Each, I believe, provide up to 15 kilovolts with the Villard doubler. So at the end, we have something like 30 or 40 kilovolts, right? Then there is a spark gap here. This is our special design. And this is kind of 9 stages spark gap, which is very suitable to provide very sharp, high frequency switch, right? Then we have forgotten tool here, and the primary capacitors are here, and this one, that's the secondary coil. In this case, we have used something with 200 terms, and the primary coils are on that part. It's not so nicely visible, right? So if we go to next slide, just for people who would like, for example, to replicate this experiment, I will give more details about this secondary coil. Sorry for that. So we kind of use the formula for the inductance calculation. This is very simple calculation for the solenoid coil, and here you have this in this table. I summarize the main kind of properties of that coil. We have 200 coils, the wire diameter 1.7 millimeter, then calculated inductance 570 microhenry. What we measure with the LRC bridge is 609, so very close, very nice. Then the important thing is that the coil should have an aspect ratio. It means the diameter and the length should be of close to 5. So in this case we have 4.3. That's fine. The wire length is 50 meter. It means that the lambda 4, so in order to have the maximum voltage at the hot end, you have to set it up such that it generates kind of the lambda 4 antenna. And in this lambda 4 frequency, in this case, is 1.5 megahertz, right? So we can go to next slide, please. in order to tune, kind of to understand the frequency matching, I was also inspired by Adrian Marsh, and we use the vector network analyzer, this DG8SAQ. That's the low-cost 1.3 gigahertz vector analyzer, which you can order from internet. I will recommend everybody who wants to do something with the Tesla transform. That's very important device. Right. So if we go to next slide. That's the example of what Adrian called the series FET, right? So we take the secondary coil as, isolated from the rest of the system, and we hook it up to this VNA, this vector network analyzer, and we use this TX output, right? And, the one leg of the output goes to the coil, and the second one is grounded. And this is what you typically see. Right, so what is plotted here is the graph. One of the x-axis is the frequency in megahertz, and on the y-axis it's either in blue is the impedance, the absolute value of the impedance of that coil, and in red is a phase difference between the voltage and current. So if you are in the resonant mode, then this phase shift, kind of what happened is the phase transition, the full swing between plus or minus 90 degree, right? So, and also there are two modes of the two resonant mode. One is serial mode. It means that you have your LC, your coil and the capacitors are in series. And if they are in the resonance state, then the impedance of such a circuit goes to 0. Or you can have a parallel mode, right, when the LC are in parallel, and then the impedance in the parallel mode goes to high value, kind of infinity. And that's exactly what we see here. In this place, which is 2.13 megahertz, we see the minimum impedance and the full phase swing, right, which is the characteristic of the serial resonance mode. And next to it is the parallel mode with very high impedance. The impedance is jump from 290 ohm to 121 kilo ohm, right? So the very high impedance and the frequency of this first parallel mode is 2.6 megahertz. And then you see the kind of replication, and these are higher harmonics, right? So this is very kind of interesting plot which you can do with this VNA, which allows you to characterize every kind of single coil before you use it for any measurements and so on. So the idea is, what we are learning as we speak is to, if you are designing the secondary coil, you have to take into account the lambda 4 effect. So you have to choose the right wire diameter. You have to choose right rear kind of diameter in order to get the aspect ratio close to the 5, and many other things like that. So, and then you measure without any discharges, just in the, without high voltage, you can kind of see the spectrum and then to decide whether it's good or not. So, next slide. Then the other kind of tuning is already involved the complete Tesla magnifying transmitter system, where you put the secondary coil inside the primary circuit, and you measure the LC primary in the parallel mode, right? So that's kind of what Adrian Marsh called the primary FET. So if we go to next slide, and this is kind of the results you like to see, right? So in blue, again, it's the absolute value of the impedance, and in red is the phase shift between the voltage and current. And what you see here is this serial resonance of the whole system, which in this case is 1.9 megahertz, right? And then you see on the left and right side of this resonant mode, you see two parallel modes, primary parallel mode and the secondary parallel mode. And they are kind of shifted by half of the megahertz or so. And the tuning now, if in this situation, is that you have to either tune a little bit the primary inductance, or if you have a variable capacitor, so you vary the primary capacitor, and you have to do it in a way such that the impedances will be of the same order, and you'll see that it's not what we have at the moment, because we kind of lost one of the variable capacitor, but right, so that's just interesting. So this is, you know, the working mode of the Tesla transformer. You see the resonant frequency, which is a serial, and then two kind of side peaks characterizing the parallel modes, right? So if we go to next slide, please. This is the snapshot from the real measurement, which we have done with our oscilloscope, where we can do the Fourier transform. And we clearly see here the peak is not very nice kind of in this. We have also some other tools to measure the Fourier spectrum. But the nice thing is that, you know, the Fourier transform shows a clear peak at 1.83 megahertz. And VNA, you know, without the high voltage analysis, shows us 1.89 megahertz. So these two frequencies are very close to each other. So I believe that this kind of shows that we understand how to tune this Tesla magnifying transmitter. Good agreement, right? If you go to next slide, and now, so what we can do with the Tesla transformer. So this picture I call what does a layman sees, right? So that's why I also, for many years, I was not really enthusiastic about doing the research with Tesla transformer, because I saw a lot of YouTube video with this kind of show in the discotheque, and people are dancing with music and with this discharges kind of, you know, so I said that's not really what I want to do in my lab, right? So if we go to next slide, but then I realized that there is actually a lot of things of what you can see. So what do I see is a new type of electromagnetic phenomena. That's the kind of snapshot from one of the experiments. You see my colleagues, Jakub Malina, that's me, and so on, when we kind of took a picture of the magnifying transformer when it's tuned to roughly 1.9 megahertz, the voltage at the end, roughly, we don't know exactly, but it's about 100,000 volts, right? And we see a lot of interesting phenomena. First, this violet, so to speak, glowing around is very beautiful. It's amazing, right? But it has much deeper meaning than what I can tell you now, right? If we can go to next slide, I didn't have too many details about that, but if you look closely how the discharges looks like, you will find that these discharges kind of are very dependent what frequency your device is tuned to, right? If you are at low frequency, usually the discharges are very abrupt, you know, unpleasant, and so on. At higher frequency, the forming of the discharges starts to be very interesting. And I'm now maybe I regret that I didn't include these slides, but you can also demonstrate that at some frequency, what you are observing is so-called golden dragon discharges, which are reflecting the Fibonacci numbers or golden ratio fractals, right? So, to my opinion, it's very fascinating. I don't have slides to support this statement, but you can find a lot of material in Adrian Marsh slides related to golden dragon discharge formation, right? So we do it as well, but this is probably yet not the time to show it here. So at some frequency, the discharges are reflecting a new, very interesting kind of physics, which is related to some fundamental properties of the space-time in the region of high tension and high frequency, right? This is for another presentation next time. So if we go to next slide, I will show you now the video from the laboratory just for fun. which we have recorded a couple of days ago. Right. So what do you see? The discharge from the hot end, right, which is not yet this fractal structure, but that's it. I think we have a longer. That's it. I think we had a longer video. Ah, sorry, thank you. You see this very nice, interesting structure and discharges over the whole, kind of the whole wire length up to the hot end, right? You know, it looks like it's not so important for free energy or whatever, but I do believe I see a new phenomena here, which are not recognized by the concurrent, let's say, electromagnetic theory. I can tell you also that we see a lot of very strange effects. For example, this is an infrared camera, and we are measuring kind of the temperature of the surrounding materials, the wire itself, and so on. And we realize that if there is a metallic object close to this transformer, then although it's completely cold, but if you touch it by hand, you will get burned. Right? Things like that, right? Very nice. So I think we can move on, if you allow me. Right. The last part of my talk I want to spend on the, to my opinion, very anomalous observation, and that research goes back to 1975. I found somewhere the references to the Kurchatov Institute paper, where people like Avramenko, Grachev, and Nikolaeva wrote a paper, Symmetry Violation of the Law of Electromagnetic Induction relative to the direction of the magnetic vector potential of the electromagnetic field. I will not go into the detail of that paper. It's very fascinating that already in 1975, you know, this is, sure, you know, all this knowledge came from Tesla, right? So it's more than 100 years old, but they were even kind of the scientific papers on this. Avramenko noticed that there is an anomalous DC potential which is created in the vicinity of Tesla transformer, and there is also the anomalous symmetry violation with respect of the direction of the magnetic vector. So I will not demonstrate here all this. So we are in the course of replicating this experiment. If you go to next slide, what we have realized that if you have a standard LC resonance kind of vibration, so it's always this oscillation goes around the zero, right? You have positive maximum, then zero, negative maximum, and so on. But what we have realized that in some circumstances, one can tune the Tesla magnifier such that you have the zero here and there is a pedestal, so to speak. So you see a pedestal, some kind of DC voltage, which shifts the oscillation towards some value, right? So it's kind of peculiar. There is a strong anomalous static potential which is felt everywhere around, you know, in the laboratory. We, for example, if we switch off the transformer, so after half an hour you enter back the laboratory and you get kind of spike of the discharges from the metallic object, half an hour after the experiment, right? And and so we see this, even if the secondary coil is grounded, so the origin of this DC potential, to my opinion, is not known, right? It generates very peculiar effects, and we can kind of measure this DC potential by the capacitive divider, right? So this I will show in the next slide. Right, so there is something anomalous that if you have, you know, right tuning in the between the primary and secondary, then there is kind of the extra kind of DC current which is circulating around this kind of system, and where is the DC current is coming from I don't know yet, but this is kind of our what we are now studying, right? If you go to next slide, we can measure, and that's to my opinion extremely interesting. We can measure this DC current by this capacitive divider, right? So we have a capacitor, high voltage capacitor, and we measure the DC voltage which is generated on that capacitor. If the electromagnetic waves coming through the capacitor is the standard wave, right? So it's oscillating around the zero, then it cannot charge the capacitors to the DC potential, right? But it does. And what we can also do, that we can change the distance between the capacitive probe from the hot end of the transformer, and then in this way we can measure the value of that potential as a function of the distance. So we measure the spatial distribution of that potential, right? So if you go to next slide, I will show you one of the video what is happening. Actually, if you place this capacitor close to the transformer, then it can get charged to arbitrary value, right? So what you see here is the voltage differential probe measured on that capacitor. And this is that one you see, and we have a discharger here, because if the capacitor goes over the voltage, it will break the oscilloscope, right? And what you see here is the voltage which is increased, and then the discharge will discharge the capacitor, right? So, and that's you see as a flash here, right? So that's very kind of standard way how the capacitor is charging, right? I believe that it's understandable. We have realized that sometimes the flashes are so fast that we cannot catch them on camera. But right, and we also measure this DC potential, as I mentioned before, as a function of the distance from the hot end. And for example, here is one measurement. We see the average DC voltage on that capacitor was of order of 3 volts, and then it grows up to 13 volts, and it drops again. And you know, that's very first measurement, but to my opinion very intriguing, because you see there is a kind of standing waves created in the free space, which is, I think nobody has ever seen that, to my opinion. And the characteristic width of that spatial distribution is very preliminary, you know, but so I didn't put any errors and so on, but the characteristic width is 28 millimeters, right? And if you then recalculate by use of speed of light in vacuum, what that would be the frequency, you will get that the characteristic frequency for that scale would be 10.7 gigahertz, right? So to my opinion, very interesting observation. So first of all, there is a standing wave formation, right? And these standing waves are made up from the static DC potential, right? And the characteristic frequency is 10 gigahertz, right? To my opinion, very interesting. So if we go to the last slide, I believe, so we are observing already now anomalies, DC current in totally symmetric circuit. There are no diodes or no rectifier, and still you have a DC component, right? It charges capacitor to infinitely high voltage. If we don't have this spark gap, then probably the capacitor will blow up, right? The DC current forms standing waves, right? Which I have no clue how come that in the free open space you have a standing wave, kind of where the maxima and minima are kind of fixed within the distance from the hot end. And the characteristic length gives you a 10 gigahertz frequency, which is, to my opinion, very interesting observation. I am not making any further conclusion besides that it's not even the beginning, maybe just the beginning. So thank you for your attention. And I think So I think we have reached the end of the heavy day today. So I would like to thank all of you for your attention, and I hope you enjoy some of the presentation. I think it is, as I said, just a beginning. A lot of new kind of interesting information will appear very soon, I believe. We have, I hope that we establish also interesting collaboration between Professor André Assis, Koen, Van Vlaanderen, Jörn is also here, and many others. So I believe that we have now a chance to dig into the details of what we are observing. To my opinion, the very important thing is to confront all this experimental observation with the different theoretical approaches to find out what is the truth, right, from the point of theory. I would also like to invite you to our next meeting, which we are planning to, that would be a big conference in April 2024, April 18 to 20, 4 days, I think, where I hope very much that we can bring Professor André Assis again here. We also have promised from Adrian Marsh. I think he is the best expert, to my opinion, in this field at the moment in the world. And so it will be an amazing event. April, please mark that time in your calendar, and I hope to see you all at this event. And let me also thank to all speakers today. It was brilliant. I'm very happy that we got a chance to organize such a small, short meeting, but very important. Thank you a lot.